Hello, everyone, and welcome to this month's Department of Energy Python Exchange. My name is Cameron Rudell, and I will be your host this evening, afternoon, or morning, depending on the time zone that you live in. As you all may know, our goal is to have Python thrive within the National Lab System and associated research sites. In support of that goal, we are joined today by our guest panelist, Dr. Rafael Ferreira da Silva, who is a senior research scientist in the National Center for Computational Services at the Oak Ridge National Laboratory, where he also serves as the executive director of the Workflows Community Initiative, which is the exact topic that he's here to share his thoughts on today. But before we get into the agenda and introduce our guest panelists, I want to remind everyone of a few key points about these exchanges. This call will be recorded, edited, and posted online. As a consequence, please be conscious of the information in the questions that you may ask to ensure that you are not accidentally sharing anything that is privileged or requires clearance. Additionally, as you all know, we are a growing community, and we would love to stay in touch with each of you. If you'd like to be kept up to date with our monthly exchanges, please sign up for our mailing list, which you can find on our website, meetup.doepy.org. You can additionally find the recordings of all past exchanges on this site, as well as a recording of today's exchange once it has been edited and, of course, posted. For those of you who have never joined us for an exchange, I would like to share with you that these exchanges are typically broken down into 4 parts. First, we'll introduce our fantastic lineup of host and guest panelists so that you may get to know them, as well as their respective fields and backgrounds. Second, we'll kick off into a coding activity where we'll ask some very applied questions to our panelists to elicit some practical discussion about best practices in software development and where they fit into the world of academic and scientific research. Third, we'll turn things over to our guest panelist, Rafael, who will share some prepared remarks on Python and the Workflow Initiative. Then, to wrap up, we will have a full discussion about the points brought up by Rafael, and we'll incorporate feedback or comments from our host panelists as well as the audience. So, if you are joining us in the audience, this is your chance to ask questions and engage with our panel to help us understand better where Python fits into the life of a researcher. With all of that being said, I will go ahead and share my screen. So, behind me, you'll see my screen. I'll, of course, hide here in the corner, and we'll go ahead and get started. For the Python Exchange, whenever we do introductions, we always lead with an Ask Me About. And the first thing that I want you to ask me about, well, is, of course, our website. If you have any questions or you want to review past exchanges, you can always go to meetup.doepy.org. Now, for our lineup of host panelists, we have first myself. Hello, everyone. My name is Cameron Riddell, and while I'm not affiliated with a specific lab, I do have a background in academic research as I studied the cognitive sciences in graduate school. For today's exchange, I would love to discuss any and all questions related to Python as a whole or specific concepts that uses Python and Python's vast scientific computing ecosystem relating to tools such as NumPy, Pandas, and Matplotlib. Next up on our host panelist list, we have Dr. Thomas Caswell. Tom, tell us a little bit about what you do and what types of questions you would love to hear from the audience today.
Hi, so I'm staff at NSLS2, where I work in the Data Science and Systems Integration Group, building data acquisition machinery for the synchrotron users. I'm also the project lead for Matplotlib, and I'd love to take questions about how to design libraries for use by scientists or visualization.
Great, thanks so much, Tom. Very excited to have you here with us today. Next up, we have Dr. Tanny Chavez. Tanny, you work at the Lawrence Berkeley National Lab. Tell us a little bit about what you do and what types of questions you would love to help us answer.
Hello, my name is Tanny, and I am a research scientist at Lawrence Berkeley National Lab at the Advanced Light Source in particular. Most of my work is mainly related to making machine learning and artificial intelligence workflows a bit more accessible to a larger scientific community. So I would love to chat a bit more about how to integrate machine learning workflows on our daily life.
Awesome. Thank you so much, Tanny. Tanny is our resident statistician and machine learning expert, so very excited to have you join us today. Next up, we are also joined by Jan Janssen. Jan, I see that you work at Los Alamos National Lab, and you are yourself a past guest panelist. Tell us a little bit about yourself and the types of questions that you would love to help us answer today.
Yeah, my name is Jan. I'm a postdoc in Los Alamos National Lab, in particular in the theoretical division. So what I'm interested in is material science and material science simulations. So for this case, I developed my own little workflow solution, that the Pyron framework, and otherwise I'm very active in the Conda Forge community, trying to produce packages for the material science community there. And so if there are any questions about Conda Forge, I'm happy to answer those, but also material science questions, or in general, I'm very much looking forward to the talk about workflows and to see how this connects to my own field.
Yeah, I'm very excited that you're able to join us with your experience of writing your own workflow manager. So we'll see how this compares with what Rafael has to share with us. Next up, we are joined by our guest panelist. You've heard me mention his name multiple times already, but Dr. Rafael Ferreira da Silva. Rafael, I see that you work at the Oak Ridge National Lab, but tell us a little bit about yourself and what types of questions you would love to hear today.
Hello, I'm Rafael. Yes, I work with mostly workflows in general. I spent 9 years of my life doing workflow systems, and now, trying to integrate better workflows into computational facilities. And I'm really looking forward, to help and discuss on the topics related to workflows, how Python has been used, to create new workflow systems, workflow managers, and how we integrate, as Tony mentioned, AI and ML workflows that are what we call the modern workflows today.
Fantastic. I'm very happy to have someone with such experience on such an abstract but useful topic of workflows, and very excited to hear your remarks that you've prepared for us today. That does take us to the end of our introduction for all of our panelists, but I do have one final message for you all in the audience. You too can become a host panelist. Email us at doepy.dutc.io, and we are more than happy to have you sit in with us as a host panelist, where you get to meet other leading experts in various parts of your research field that use Python. Or if you know someone who wants to become a host panelist, you can also send their information our way or share our information with them. We're more than happy to keep adding to our list, our growing list of panelists. Why don't we go ahead and jump into our coding activity for today? For today's coding activity, we have a fantastic game of When Do I Use? Here's the rules. Well, here's the preface, I should say. The preface is Python's open source ecosystem is massive. And as its varied tooling has grown, we've seen numerous different attempts at tools that occupy an overlapping problem space. I'm willing to bet you can think of some just off the top of your head already. Today, the panelists and myself and you in the audience will work together to determine when and why we should use a specific Python tool. So our panelists will be presented with many existing tools that have overlapping coverage in a problem area. We'll provide guidance on whether there exists some logical steps to separate or disambiguate when we should use one tool over another, or if one tool rules them all. And then lastly, we will, of course, score our panelists. No, I'm kidding. We won't be scoring any of our panelists' comments, but we will be providing some relatable anecdotes and experiences working with some of these packages and tools. So let's go ahead and dive into our first round. Round one is all about data frames. Python has a vast number of data frame libraries, but they aren't all built the same. There are even a few runner-ups that I haven't mentioned on this slide, just because everybody at some point wrote their own implementation of a data frame. And I would love to hear from my panel. Let's pick two of these for a comparison. Pandas versus Dask. When would I even think about using one over the other?
Yeah, so Pandas and Dask, it's interesting because I did some data science in the past, and Panda, for me, it's very simple to use. It's very straightforward. You can start creating data frames, start doing a lot of analysis. However, you can quickly run into memory intensive issues if you have very large data sets that you're trying to process with pandas. While Dask, it's more really doing a distributed way, in a parallel way. And my experience is you can really scale it up to thousands of nodes, for example, into an HPC system. At Oak Ridge, we use Dask a lot for processing several kinds of workflows that are doing, distributed analysis of large amounts of data.
Awesome. Thank you so much, Raphael. I think that's a very fair intuition of Dask versus pandas is when the data just no longer fits into your single computer's memory, well, you have to use some sort of distributed solution. And I have spoken with people who have told me about how they got multiprocessing to work well with pandas. And I'm like, oh no, you should have just used Dask. You wasted a lot of time probably. But with that being said, I would love to hear from any of our other panelists who want to compare any two of these things. And if not, I can speak a little bit about pandas versus polars. Polars is probably the newest data frame tool on the block, at least in terms of what's up here. But pandas is a very robust tool, and it's robust in that you get exactly out of it what you put into it. This means you can have extremely slow computation if you've chosen an inefficient approach, or if you're using some common, what pandas calls anti-patterns, right? Pandas-specific anti-patterns. My main thing with the difference between pandas and polars is that polars has a different API. It has an expression API, and these expressions are, in general, lazily evaluated. This allows it to simplify those expressions and perform nice cache optimization so it doesn't have to repeat any computations. And on top of that, I think overall that approach to an API, it makes it harder to do the inefficient thing or do the slow thing. And that's one of the things I like about polars. But when it comes to I have a data set and I just need to keep working with it, massaging it and working with it until it kind of bends to my will into the shape that I need it to be, pandas you're going to have a lot less roadblocks with pandas. Whereas since polars is still fairly new, I would anticipate seeing some roadblocks when trying to do very kind of minute things with it. But I think that takes us to a good conclusion for round one, data frames. Let's go on to round two. In round two, we're going to discuss some different execution models, parallel and concurrent execution. And there's a lot of different libraries. Most of these come pre-installed with Python as part of its batteries included features. I'd love to open up to our guest panelists. Pick any two of these and tell me when you might use one of these over the other.
Maybe I can start. So multiprocessing, or I guess the parts with the multiprocessing versus the concurrent futures, right? And while it's usually easy to get started with the multiprocessing, have your first maps and applying to data, at least for simulation, we typically have the case that not all simulations take the same time. And so you definitely want to go to a futures-based model to have this kind of asynchronous part when the task's finished. And that's really like, for us now, more or less the default, trying to teach people to think about the futures and adopt the futures pattern in their tools.
Yeah, I think that's a great point. For those of you who haven't used multiprocessing or concurrent futures is more or less a wrapper around multiprocessing, but it gives you a nice API that's has composable elements, and as Jan mentioned, the futures-based API.
Well, I'll take. Oh, sorry, go ahead, Rahel.
Go ahead, Tom.
Go ahead.
So I'll take async IO and threading. Unlike the others, these are both in a single process and how I would pick between them. And so if you've got a task that is IO bound, so that is you're mostly waiting for somebody to respond to you, I would go for async IO for the concurrency. So like if you're hitting many web servers or many URLs to get data back. However, if any of those tasks hold the GIL for a particularly long time and are going to do heavy compute in that task, because async IO is single-threaded, you'll end up blocking the event loop and actually lose efficiency that way. Whereas threading, if you're doing things that are wrapping some underlying native library and will release the GIL when they're doing work, such as some parts of NumPy, SciPy, and Pandas, then threading can get you actually saturate your cores all in one process. But of course, then once you're dealing with threading, now you have all the complexity of dealing with a threaded application. Whereas in async IO, because it provides this essentially linearized view of your program, it's much more easy to reason about.
It's a fantastic summary of the differences between those two. I often summarize it in terms of async IO gives you the ability to tell the program when you want to switch what's being executed, whereas threading, you just let your operating system handle that. Any other comparisons? Raphael, I saw that you came off mute a moment ago.
Yeah, it's very similar to what they said. I just wanted to emphasize, for example, the concurrent futures. It's very used in workflows, or when you have a DAG in simulation, that you're trying to see. You need to work with what is going to happen with something in the future, but you cannot run it now. So future, it's very much used, the way that you can assume that you're going to get an answer that, so you can start already, organizing with, for example, that node in the DAG. And then when you get the result, actually, then you can actually process that part of the workflow. So just to emphasize that, it's very, very much used in most of our workflow systems built on Python.
Fantastic. And all of this talk about concurrent futures has me thinking, I think I've been using it wrong. So hopefully at some point this topic comes back up and we can talk a little bit more about the futures-based API within the confines of a workflow, because I think this is a fascinating topic. But I'd say this does round 2 justice. Let's go ahead and move on to round 3, statistics. Python, as of, I want to say, either 3.7 or 3.8 got an upgrade to the statistics module. And so Python has some nice C functions for built-in statistical operations. Now, this isn't going to be exhaustive, but we even have abstract notions of distributions now built into Python, which is quite nice. So we have our choice of the built-in statistics module, the stats models library, the scikit-learn, very popular library, and of course, SciPy. Now I'd like to open it up to our panelists to pick any 2 of these and let me know, when would I use one over the other?
I think I would like to agree that there is a lot of overlap between many of these libraries. For instance, for example, if we were to compare scikit-learn versus SciPy, for example, I will probably say that it also depends on what type of data we're handling and what is the algorithm that we're looking for. Because as much overlap as there could be between these two, some few algorithms might be available in just one of these packages. At the same time, for example, if we're handling images and we're handling like large volumes of images, we're gonna go probably for scikit-learn maybe. Whereas, for example, for more of a linear analysis, one-dimensional analysis, maybe another library might be a bit more suitable. I have myself falling as well for the option of just building my own because I didn't want to trust at that time many of these libraries. I wanted to make sure that the algorithm was put together the way I knew about it. Will not recommend that. I think that overall will be good to check on the source code and documentation that is out there just to make sure that we understand every step of the process and we consider those whenever we're applying any of these algorithms.
Fantastic. Thank you so much, Tanny. I think that's really good insight onto when I should use scikit-learn versus SciPy. And I think one of the biggest factors there, in my opinion, is that scikit-learn has a nice uniform kind of fit transform-based API, whereas with SciPy, all the methods are going to be named something odd and something different that you'll have to really go digging for. And then the output is going to be something that's unique for every single function you call. Any other thoughts from our panelists on these statistics libraries? All right, if not, I do have one comment. The stats models library is quite different from what you'll find in scikit-learn. Stats models actually used to be a part of SciPy way back when it was first created. It was, I believe, scipy.models. And stats models, if you have a background with R, I know this is a Python exchange, but if you have a background in R, SciPy has a full extension of, quote, the formula-like syntax that R has to offer with its formula mini language. And so if you like using formulas to define your models, I think it's a very nice shorthand. And stats models will compute p-values for your test statistics for you. Whether or not that's something you want to be doing, well, I'll leave that to you to decide. But stats models does have a lot of conveniences in for it. Let's go ahead and move to our final round, data visualization. Now, over the last 2 decades, Python has seen a wide number of different data visualization toolkits. With this many choices, how can I just pick one? Now, I'd love to open this up to our panelists to pick any 2 or pick any 3 and let me know when I should use one over the other.
I feel I should jump on this one.
Do you feel obligated?
So I think if you're familiar, so Seaborn and Plot9 are both libraries built on top of Matplotlib that provide much more specialized interfaces to plotting. Seaborn really is based around statistical plotting and the kinds of things you want to visualize when you have tabular data of the kind that is very common in the fields that like Roscom came from. And Plot9 is a implementation of the ggplot plotting API on top of Matplotlib. So if you like that API or you have that kind of data, definitely use those libraries on top of Matplotlib because they will make your life better and faster because you'll get, usually your goal when plotting is not to enjoy the plotting library, is to see something about your data on the screen as quickly as possible. So please opt for the tool that gets you to graphs as quick as possible. And I guess on the other side, Matplotlib, if there isn't a high-level tool that just does what you need, Matplotlib can almost certainly make the figure you want. It's just a question of how complicated it will be to reproduce it.
Mm-hmm. I think that's a great summary of the kind of the high-level APIs versus the lower-level API that Matplotlib has. Because sometimes just getting something relatively simple out, that's all you need, right? If I need to create a quick bar chart with an error bar, well, I can just use Seaborn, the bar plot method, and that does a lot of the heavy lifting for me. Whereas if I wanted to create this on my own, well, now I need to go calculate my own intervals, whether I want to use standard error of the mean, standard deviation, or some bootstrap confidence intervals. I would have to do all that by hand and then add that as an artist or a feature to my plot. Any other comments from our panelists for some of these other tools? I know that Plotly and Bokeh are both for, not going to say interactive visualizations because Matplotlib does have interactivity components, but if you want to be interactive and on the web, then you should reach for something like Plotly or Bokeh. Polyviews is a high-level wrapper for Bokeh, similar to the way that Plotly Express is a high-level wrapper for Plotly. But Raphael?
I'm not an expert on visualization, but I have an anecdote on that. So as you said, Plotly and Bokeh are for interactive. We worked on a project a few years ago that we were trying to build, large visualizations. And then we started with Plotly because, the simplicity that it was, and there is a lot of documentation, a lot of people with providing examples. But we quickly ran into, scalability issues. And then when we deployed Bokeh server, that it requires a little bit more work to get it done. But it could handle much larger plots, and for the interactivity through the web. So I don't know if we did something wrong, but that was our experience.
Yeah. Now, I've never deployed something at a large scale to hit either of those kind of balance issues, but that's a very good feature to be aware of. At least when you did this, that Bokeh seems to scale just a little bit better than Plotly. But that does take us to one question in the chat. Which package should we use when we care about fast live plotting? I believe you can, if you're trying to do some streaming data, you can do that with either Plotly or Bokeh. Depends what you mean by fast, but here both of these libraries all the drawing is done on the front end in the browser. So if you're updating data from a server, it's really just sending those extra data values across. So it's a very small package that you're sending. And I think the key thing here is that your network latency is going to be what determines if it's going to be fast or slow. Since the packages that we're sending are quite small, you might need to implement a little bit of buffering or something on your end just to keep the plots updating what feels responsively. But great question. That does bring us to the end of, oh yeah, Tom?
I was just saying, so depends on the context. If you must have it in the browser, probably Bokeh Plotly is a better choice. You can have it on, if it's on a client application, Matplotlib can do streaming, and with a little bit of work, you can easily get 60 frames a second. And if you need far faster than that, I would look at PyQtgraph, which uses GPU acceleration to get, truly blinding speeds on even very large amounts of data. But that obviously, again, it's a Qt plotting library, so it needs to be on a native machine.
Yeah. Yeah, I think that's a really good point, is if you're having a lot of data come in very quickly, having something native where you don't have to deal with network latency will always be the best choice. But that does bring us to the end of our coding activity here for the day. And with that being concluded, I would love to turn the reins over to our guest panelist, Dr. Raphael, to hear what he has to share with us about workflows and the communities built around it. Dr. Raphael.
Thank you very much for the invitation. Let me see. Let me know when you can see the slides.
Yeah, we can see them.
Okay, great. So yeah, I'm going to talk a little bit to you about the Workflows Community Initiative, what we have been around, trying to make it into the context of Python and how Python has been important into workflows. And also talk about one of the tools that we developed called SciJ, actually the Python reference implementation for this tool. So I don't know if you are familiar or not with workflows. Workflows is such an overloaded word today that can mean everything or nothing. So the way we have been supporting today, it's computational workflows, and see how we can enable DOE science through these workflow applications. So there are two different ways we are characterizing our workflows. This is what we call the traditional scientific workflows. So they have been around for over 20 years and have enabled several breakthrough science. So the way that it works normally is you have these DAGs that are classical graphs that you have, the nodes of the DAG normally represent a task in the workflow that is going to do some computation, can be a simulation, can be a visualization task or something. And then you have the edges that are normally the dependencies that typically are files, but also can be control dependencies, can be data streams, and so on. So these traditional workflows, have supported several things like a Nobel Prize for the gravitational waves, the Higgs boson, and also, with the COVID that we look like we are, getting out of that finally. And with COVID research, there were so many workflows that were supported and enabled to try to figure out, and help with find the vaccines, understanding the transmission, and so on. So these are what we call the example of traditional workflows that are, up to today, they are extremely important and they are still there. But there are also what we call the modern scientific workflows that Tanya was mentioning. She's working with AI/ML kind of workflows. So these modern workflows, why we call it, because the traditional way you would have that DAGs, and it'd be quite easier for you to think about, say, oh, I want to do an optimization on these workflows. So basically, I know exactly the entire DAG. I can come up with some optimization algorithm, do some scheduling, and provide my resources, do the runs, and get everything done. With the modern scientific workflows that we're seeing today, everything now becomes much more dynamic. So you start running the workflow, there are the human in the loop. So the scientist is always there looking and trying to understand what's happening. With the AI/ML tools, you see that you need to be trying to optimize something, trying to get into see if you got a threshold that was satisfied or not, and then you keep going back into several loops. And this becomes a lot of more challenging for the workflows research itself, because it's not that easy for you to go and just say, okay, I know my entire workflow, how it's going to look like. I know how much resources I need. And right now the question is, I don't know. I know the starting number of resources that I need, but I don't know what's going to happen throughout the execution of that workflow. So there are several Python solutions that have been developed, and especially into the AI/ML world, there is a lot of solutions in Python that have been used and incorporated into the workflows, and that it has really helped the scientists, and making it much easier to interact with the machines through the APIs, the interfaces. There are new kinds of workflows too that are involving needing more than one kind of machine to run. So you involve cloud, HPC, edge. So you need to make the connection across all of these things. So based on that, there is what we call the universe of workflow systems that have been developed. Workflows have been developed since the end of the 90s. It's when they started the first, drafts of workflow systems to really support the executions of these applications. Of course, several of them, there are a lot of them that were developed based on C, C++, Java, but today with Python has an explosion of workflow systems, that are based on Python, that are especially integrated with machine learning and AI tools. So on this URL here, and I'm happy to share these slides after, they are trying to keep a collection of how many workflow systems have been developed up to date. I checked yesterday, and actually up to date, it cataloged 334 different workflow systems. And as one of our panelists mentioned, they developed the whole system. Maybe we should add at least two, so it'd be 335. Of course, there are needs for several different workflow systems. Most of them start, as a small project that is really focused in solving one specific problem, and that other systems normally they are not well designed for that. And then, with time, say, hey, I could try to optimize, I could try to generalize this my approach, and then you try to become with a system that is more and more generic, and of course, start to become very similar to other systems. And the problems that we have today with this number of workflow systems, this universe, is they are very useful. They do a lot of good work, but they're very hard to be used. So, there is a scientist from Berkeley that Tani might know her, Lavanya, that said this sentence, and I kept this, that it says, a workflow system today is so hard to use that you need a developer to be shipped with the workflow system. It's the only way that anyone can know how to use it. And, there is all this kind of overload problem of this amount of workflow systems. So if you look into the architecture of the systems, and I'm not going to go into the details in these presentations, but typically what they are trying to do is you have a workflow description, you have some task manager that is trying to optimize the description of that workflow. If it's static, it's easier. If it's dynamic, you need to always be reevaluating what is happening during the execution. And then, you're going to try to dispatch it to run into some system, into HPC system, or a cloud system, edge, or even your now local machine, local cluster, your laptop, and so on. The one problem that we see with this kind of things is that, for example, even if you go for an HPC system, there are different ways you can interact with that scheduler. There is Slurm, there is LSF, the PBS, Cobalt, and so many other different options. Flux that it's coming to become the scheduler for the next Livermore machine, El Capitan. And how do you know all of these? There are different interfaces. Each system is developing their own solution on that. So I'm going to talk about a little bit later about SideJ, that is our solution to try to solve this problem. And so the problem is when you have this universe of 300 something workflow systems, we got to a point that things got too much disorganized, and we were trying, to have a better idea on how we could have the community working together to solve a specific problem. So we knew that we could not say we only need 1 or 5 workflow systems. We know that it's gonna, have several ones from different needs, but at least we could try to bring the community together to create a community roadmap that would, emphasize into some of the challenges, what is the current state of the art, what is missing, what are the short and long-term actions that we can take to work partially together. Some of the folks, can team up and try to solve some issues, and others might, solve other parts of the problem. So in 2021, we did that effort. We had an event, online event, that we have a lot of folks coming from across the world, people that we use workflows. We put this together. We identified, several challenges. The paper had all the details and on different areas of things that we would need to address. And there are 2 main things that are these 2 things highlighted here with the arrows that I'm going to talk here in this particular presentation. That was the challenge of having this ill-fitted job abstraction that I mentioned before. Every single workflow system developed their own solution on how they're going to talk to different schedulers, and the need for a workflows community. So people, could work together, have a single point, a single place that they could go and find information about what is happening with the community. There are working groups working towards solving a common problem, and so on. So based on that, beginning of last year, we created the Workflows Community Initiative. It's an 100% volunteer-based effort. So we have no sponsorship, there is no fees, anyone can become a member. So up to today, we have 176 people that officially joined the community. You go there, you fill a form, and that's all. And you get, information about newsletters, events, information about working group discussions, and so on. And we also have a Slack channel that it's open to the entire community that we have. I think last time I checked was 470 something people that are discussing about, questions about workflows. They have side channels that they can go into more specific discussions. So the idea really with this initiative was to bring the people together, have discussions, and keep, at least producing once a year a report, or that we can turn into a paper to inform, the community and funding agencies what are the needs for workflows. So last year, end of last year, we did the what we call the Workflows Community Summit. It was in 2022. This was 2022. In March this year, we produced the report, that had over I think about 106 or 107 authors in the report. Everybody that attended the event became a co-author. And the idea is, I'm not going to go into details. You have the DOI for the report if you're interested in that, or you just Google Workflows Community Summit, and you can find the report from last year or even for the 2021 editions that we had too. But basically, we are looking into identifying, standard specification, APIs, high performance data management, in situ workflows, what are the needs there. And everybody's always keep talking, we need to define common terms, we need to define common schemas, we need community-driven efforts. The hot topic now, everybody talks about HPC and the quantum workflows. That is, everything is too heterogeneous. Even on the quantum computing side, they have there are still limited the machines that you can have access to. For example, at Oak Ridge, you have access to free machines, but we have a limited budget to run things there. It costs a lot of money even to run a small experiment. So there are things that I think we're still in the early stages of HPC and quantum. Then there are the AI workflows, and again, the community is saying, common terminologies about the different motifs on AI workflows, trying to do the integrations, benchmarks on every single thing. It's basically missing today. We have benchmarks for so many different aspects of CPU, IO, networking, but we don't have workflows. We have developed a first one, but it's still in the baby steps for what we need to achieve. So fair workflows, how we make all of these into, in a fair way that data can be accessed from the execution of these workflows. And the continuum and cross-facility workflows that what I mentioned, workflow that it's involving different user and computational facilities, how you make the communication between these different sites. There is all the policies issues and things related to that. So this report summarizes these discussions, provide a bunch of different recommendations. And normally what we do at the end is share these with as many funding agencies that we know to try to inform them what the community is saying, what are the needs, and hopefully, help them develop programs, develop their needs on the next steps. So this is all the political part. More into the practical side. So as part of the ExaWorks project, that is an ECP funded project, DOE ECP, we start, working with putting together different workflow systems, workflow tools to build an SDK to try to democratize, access for how users could start using workflow tools. Some of these tools are developed in Python, and some are, for example, Swift-T is mostly C++, because it's looking into the optimization for HPC code. But Parcel, Balsam, Radical also has aspects of Python. So the idea is really how we could integrate these systems, that it would make much easier for the user to develop. One thing that we got there when we start, doing these integrations, we discovered that every single system, and as I mentioned before, had a different way to interact with the scheduler. So they come and said, okay, for example, Radical has a tool, a whole layer, to communicate with different Slurm, with the cloud systems, with the LSF, Cobalt, and PBS, and so on. And Parcel had their own too. So based on that, we, saw that there was a need to have a common interface, a common layer that we call SciJ, that it's basically portable submission interface for jobs. And the idea with SciJ is you just need to define your job using SciJ, and then SciJ would automatically, translate your job definition into one of the schedulers. So the idea is we would like to remove from every single workflow system these handcrafted layer that they have, each person did their own, and replace with SciJ. And when we have a new scheduler that would be released in the future, we would just, extend SciJ to support this new scheduler, and then all the workflow systems would benefit from that. So to start this effort, we didn't do ourselves only. We created a problem definition. We, worked with the community. We had about 70 to 85 people joining discussions to create a community specification of what it would mean, a job to be submitted to these systems. And then we went through a whole process, open discussion using GitHub to come up with a specification. So once we had that specification, what we did is say, okay, let's implement it in Python and have a reference version of it. So today, if you go and you do just a simple import of SciJ, or JSci actually, that it's how the Python package is called. You can directly, create an instance of the executor that you want to have. So for example, today we have PBS, Slurm, LSF, Flux, and Cobalt, and we are expanding to 5 more at this moment. And when you create this instance of this executor, basically the only thing you need to do is, are you using Slurm? Do you want to be using LSF? Using Flux, and so on. And then you have, the definition of your job specification, that is going to be exactly what are the things that you want to run. So here, for example, in this left side of the slide, It says I create a job specification that I'm going to run a command that is very simple, sleep command, for 10 seconds. And that's all that is going to be my job. And there I'm going to say, I have a job range and I'm going to create this job, submit, and wait for the result. When the job is done, I have it back into my system. Of course, this is a very simple implementation here, but the API, has been improved, and now we can provide basically every single thing that normally you would put into an HPC job, for example, you can do through SciJ with specifications. So if you wanted to define environment variables, basically you just put, you have your job specification, you have your environment, and then you set as many variables you want to set. If you want to pick up, the standard I/O, you just set up the paths that are where, it should be written. And if you need job resources, for example, number of CPUs, the process how many processes you want to have per node, and so on, you can do all of that with a job resource specification. The good thing is all of this is abstracted from the user that doesn't need anymore to have the specific knowledge of that specific system. And even here, for example, you can also set up for a few things. If you go for systems like OLCF, NERSC, or ALCF, you need to have a project number, an allocation. So all of these, you set up as part of your job specification. That is very generic. You don't need to care about the system's details, and these are going to be automatically translated to your execution. As you saw in this first example here, we could just use the wait, and then you have it's going to be basically asynchronous execution. That when you get to that point, it's going to be waiting until the job is finished, so then you can go to the next level. Or if you want to have something more dynamic, you can have status callbacks. And the idea with the callback, we are using basically here the filter that we discussed in the beginning under the hood, that basically you submit the job is released, and when that filter gets completed the status, it's gonna call back into it's gonna inform you that the job is done, and then some action can be taken. So one thing that is an important message that we learned recently was initially when we developed SciJ was really focused into replacing that layer that workflow systems would use to communicate with the schedulers. However, we have more and more users today, from workflow systems that are actually scientists. They are developing, their own scripts to run their experiments into several of these DOE systems. And they said they were tired, and saying, oh, every time I need to have my script, I develop one to run on one computing facility, but when I go to another computing facility, I need to adopt my script because the schedule is completely different. And these folks now they are very happy enough using SciJ, because they say, well, I just specify it once, and the only thing, for example, would have to change is the type of executor that I wanted to use. And another message that we want to say is when you should not use SciJ. If you're not looking into portability, so you always run your code into the same system, into the same computing facility, you don't need to learn about SciJ, to be running code there. You can just basically go and use the directives provided by your own scheduler. But if you really look into portability across different systems and have something, that you release and other people can pick it up and potentially run into their own system in a seamless way. So we would strongly recommend people to start using SciJ. So with that, just some final thoughts where we go, towards sustainability of these workflows. So I don't know if several of you heard about it. ECP project is ending. There are some seedling efforts on DOE regarding sustainability, sustaining some of the DOE software that supports DOE science. And we are leading one of them that is about workflows and application services that we are really looking into software that it's supporting all kinds of workflow applications. So this includes the workflow systems, so data management frameworks, visualization frameworks, AI, ML tools, and not PyTorch and TensorFlow itself, but things that are built on top of these tools to enable science. So, for example, the things that Tani was mentioning, and application services in general, like cloud services, APIs, and so on. So if you're interested, feel free to contact us or contact me directly, that I'm happy to talk more about this. With that, I'd like to thank you all for your attention. And if you have any questions, I'm happy to answer.
Great. Thank you so much for sharing. I would love to open up questions from our audience. So if you have a question, feel free to enter it in the chat or in the Q&A widget. And then also invite our host panelists back to hear some feedback, some thoughts, comments, or questions that you might have for Raphael.
Yeah, maybe I can start.
Yeah.
So we had a lot of these issues, right? So we also developed our own queuing system interface. We are very happy with Flux, right? So Flux is really what's pushing our jobs now. We really like their Python bindings and their ability to run it within any other queuing system. What I would be interested in, so my typical workflow has like 4 different kinds of tasks. These are serial Python tasks, MPI parallel Python tasks, or serial executables which have no Python bindings, or MPI parallel executables which have no Python bindings. And what I find in many traditional workflow tools, talking about Dask or so, is that they don't support the MPI parallel execution model. It's like where certain tasks or certain substeps of my workflow need to run in MPI parallel. So is this part of your workflow language, or can you maybe comment on this, how to handle MPI parallel subtasks of your workflow?
Yes, so SciJ allows this, but for example, for the level, if I'm understanding well what you're trying to look for, I would recommend you to look into systems like Parcel, PARSL.
Yeah.
That is developed it's a full Python-based system, but it has a very nice integration with the MPI aspect there. So I would definitely take a look there. Another one, let me see, SwiftT also has a very good angle into MPI, and it's optimized for that. And even though SwiftT is not developed in Python, but they have Python bindings. So you can, specify your code in Python and then compile into SwiftT that is going to be optimized to run in the HPC systems.
Very nice.
Anything else from our panelists, Tani or Tom?
Yeah, I think that my question might be just a more general question. So I think that you mentioned before as well, for example, when it will be suitable or not to utilize that package. I was wondering in this case, for example, when it would be like the general limitations in terms of its application of its usage. Something that I was wondering, for example, is how versatile and like how much customizable it is once the workflow is already on the run. So like once it's submitted, does it work exactly as any other scheduler out there, or are there like other possibilities of making changes like on the fly as we see the results coming out of the pipeline? That's something that I myself will be interested in hearing more about.
Yeah, so basically, yeah, that's the challenge of what we call the modern workflows, because have these interactions, you need the callbacks to the users. So, for example, solutions like MLflow, they are providing, I would say, the first step to provide this kind of things, because they're very tied with a lot of the ML packages, and it's 100% developed in Python. Very tight integration with Python tools. However, MLflow has a lot of limitations into DOE HPC systems because of it's not because MLflow, but it's because of the policies of these systems. that for these things you need, for example, when your jobs are running, into the compute nodes, you need some way to get information back. So you can coordinate, or sometimes even externally, not only to the logging node. So, but a lot of DCs, they don't allow you to get, from the working node outside the outside. So there are some solutions. People are working through these things, some ugly solutions involving like SSH tunnels and so on. But but there are some Python packages for that. Actually, we were exploring one in one of our use cases. But yeah, it's still, I would think, it needs more research to get it done. But we are going there.
Very nice. Thank you.
Tom, anything from you? If not, I do have one question.
Yeah.
I know that many different companies or individuals, researchers, pretty much everyone has in some way or form probably implemented their own kind of workflow system. I know I did a very, very odd one back when I was doing research on fMRI data. But I'm curious, for those of us who are trying to roll their own and maybe, it's never going to be the best thing, how can we get in touch with you or with the workflow community?
Yeah, so that's a great question. That's one of the main reasons why we decided to create a community. So what I would say today, if you can go into the workflows.community is the website, and from there, or join the Slack channel, or both, join the Slack channel and become a member because you get a lot of information. But the Slack channel, I would say, is the easiest way to put your question there. Say, hey, I'm looking to do this kind of workflow, and can someone help me with that? One problem that we see today, and I don't know if it's only the workflows community, but or everybody that develops softwares, is whatever workflow system we're going to talk to and ask, hey, I have this problem. Would your workflow solution work for me? Everybody's going to answer yes. The thing is, we can always make a problem fit a workflow solution, a workflow system. But if that is the best, match, that's another question. But we can always make it work. We can do hacks and make it work. So I would say, go into the community, put in, a question like that open, that we have a Slack with 400 and something people. You might get, 10 different people going back to you, and you can start, talking to them and say, hey, but my point is really that, well, how can I enable this thing? And when you start to see that people can say, yeah, we can do this, I said, okay, maybe that's not the right solution. I might go to this other system. But we, as the community, we are trying to create a place that users can come and start learning more about the workflow thinking. This is what we say, the way how you think it to do workflows.
I love that because it's a very different form of thinking than, one, if you're a researcher, anything you've really done in research, but two, even if you're a programmer, thinking about workflows is quite a different mode of thought because the execution model can differ depending on what you're trying to accomplish. And I think the best part about having a community is that chances are, whatever you're trying to do, somebody else has already tried to do it, and they know, where you're going to run into walls or where it's easy, or where tools like SciJ can very easily solve your problem.
Exactly.
Awesome. Well, thank you so much, Raphael. This takes us to the end of our exchange this month. I did want to have one final round of applause for our guest panelists. Thanks to Raphael.
Yeah, thank you.
Yeah, thanks for joining us. This has been such a fun time. For the audience, make sure that you tune in again next month when we'll be joined by Dr. Leah Wasser to talk about the importance of Python in the open science effort with her organization, PyOpenSci. In the meantime, you can watch out for updates on our website. That's meetup.doepy.org. But until next month, thanks everyone.